All right, so here we're going to begin this new chapter. This is chapter 6, unit 6, and it's called integration. We're going to start off this 6.1 with this idea of the antiderivative. At the beginning of the course, at the beginning of the semester, we did a lesson where we went through this worksheet, and it said, okay, this course is going to be divided into two halves, and the first half is going to be differentiation. And so that's what we've been doing up until now. So that's included learning about limits and how to evaluate limits. We used those limits to be able to find the slope of a tangent to a line. And we decided that, okay, so that is our slope function, taking a derivative. We use that for, we used it for all kinds of applications. And then we developed it to go beyond just polynomials, but then we did trig functions and we did exponential and logarithmic functions that we could use this derivative on each of these functions to solve all kinds of various problems. So that ended up being essentially what we've been doing in this course up until now. Now from here, we're going to take a step further, and we go and we look at something called integral calculus or integral calculus. What this ends up being is this ends up being kind of differentiation going backwards. And so it is called antidifferentiation, or it's called integration. Those terms are pretty much interchangeable. Instead of finding a derivative, we're going to now find an antiderivative. The notation that we commonly use is we will use this idea of f of x, and we'll use capital letter F. And it ends up being such that if we take the derivative of that, it will be our normal lowercase function f. Which means that if we're given f of x in this case, and we're asked to determine what f is, then we can do that. So in this case, f of x is equal to 10x. Well, if f of x is equal to 10x, that's the derivative of something that we started with. Then what did that something we start with look like? The first step that we need to take to figure out what it looks like is realize that when we differentiate, our degree goes down by 1. When we first did these, we differentiated x squared and realized that, okay, I subtract 1 from my exponent on x, and I'm going to multiply my coefficient by that. And so when I differentiated x squared, that became 2 times x to the 1. So if we now have f of x is equal to 10x, so that was degree 2. So let's call this capital F of x. And let's leave a little bit of space, and let's call this x squared. We're going to leave this 10 out in front, but it's not exactly 10x squared, is it? Because if I try to differentiate 10 times x squared, I would be multiplying 2 times that 10, and I'd have 20x. So I also need to divide this by 2. When I divide that by 2, this gives me 5x squared, which is what we desire to have. So our step is going to be undoing what we were doing before. What we did before, we subtracted 1 from our exponent and then multiplied our power by the coefficient. In this case, now for undoing that, we're going to add 1 to our exponent, and then we're going to divide by that also. Now, the problem though is this, is to call it just f of x, or capital F of x, is equal to 5x squared is not quite right. Because what if I had f of x is equal to 5x squared 4? If I differentiate that, I also get 10. What if I have 5x squared minus pi? Any sort of constant that we add or subtract from this 5x squared, when we differentiate it, we'd still get 10x. So all of these are essentially correct. And so what we call it is we say that capital F of x is going to be equal to 5x squared plus some constant c. So we'll use this idea of constants of our constant letter c. This ends up being called our indefinite integral. And for now, we'll just be using indefinite integrals. Later on, we'll see when they're no longer necessary to have and why that is. But for now, we're going to call this our indefinite integral. And the reason that works is because if I have 5x squared as a parabola, and if I compare that to 5x squared plus 4, or 5x squared minus 7, or 5x squared minus 12, or whatever, all of these curves look the same. And for any given x value, our slope is going to be the same on any of those. And because the slope is the same on any of those, then the derivative is the same on all of those. So when I take my derivative of 5x squared plus c, it doesn't matter what the c value is. The derivative is just going to be equal to 10x. So we have a table here that has a few different rules of what this is going to look like. If our original function is just a constant function, f of x is equal to k, then this one's nice and simple. Then capital F of x is equal to kx. So for example, if f of x 7, then capital F of x, antiderivative, would just be 7x. We can't forget about adding c on the end, but it's pretty easy to see that to differentiate 7x, we would get 7. So kind of straightforward. The power rule is that what we just did with changing 10x into 5x squared. We know that we need to add 1 to our exponent. We know that this has to be 1 more. And so we're also going to have to divide that part out. The k stays right where it is, and then it ends up being divided. In our case, we were looking at 10x, and that was 10x to the 1. So I added 1 to the exponent, called it 10x squared, and we divided it by that same number that we have as our new exponent. And so that's what we did in this case. With e, remember that e to the x, when we differentiate it, it's also e to the x. If we have a constant in front, a, that doesn't change. But if we had a constant as part of the exponent, e to the 3x or e to the 5x, by chain rule, we would have to also multiply that by that part. If I had y is equal to e to the 7x, I'd differentiate that, I would call it y prime is equal to e to the 7x, but then by chain rule, I'd have to multiply that by 7. So because of that, when I'm doing an antiderivative, when I'm going backwards, I'm going to have to divide out that 7 in this case. So a stays the same, a stays where it is, e to the kx stays as it is, but if I have a constant, if I have a coefficient in my exponent, I'm going to divide that piece out, and then plus c. Natural log is kind of straightforward. Natural logarithm, remember the derivative of natural log is 1 over x, and so if we have 1 over x as something that we are trying to integrate, then it's going to be natural log of absolute x. We need the absolute value signs on that, just because in this function, x may have been positive or negative, but it cannot be. We can't take the natural logarithm of a negative number, and so we have those absolute value bars around our ln. And then the last ones here is just what's going on with trigonometry. Remember that the derivative of sine was cos. So therefore, if I'm taking the antiderivative of cos, that's just going to end up being sine. But because the derivative of cos was negative sine, if I'm taking the antiderivative of sine, it's going to be the negative of cos. So it just ends up being going backwards from what we've seen before. These boxes over on the right, all that's getting at is kind of similar to what we saw up before with with chain rule, is if we have cosine of kx, then we're going to have sine as your antiderivative of kx, but we're also going to have to divide that by k, because if we were differentiating, we would be multiplying it by k. So let's see what these look like. Example 1, 2x cubed plus x is f, capital F, so the 2 stays the same. We add 1 to the exponent, and then we divide by that. 2x to the 4 over 4. Plus, this is x to the 1, so we add 1 to that, and then we have to divide by that amount. We can't forget plus c, and let's just take a step and tidy it up. 1/2 x to the 4, 1/2 x squared plus c, or x to the 4 over 2 plus x squared over 2, either way. What we're getting at here to do a check is let's take the derivative of that as we got as an answer. Capital F of x was half x to the 4. So if I differentiate that, that just ends up being 4 over 2 times x cubed. That 2 multiplies, comes down front, so 2 over 2. Subtract 1 from the exponent, that's x to the 1. And then the plus c, when I differentiate that, that's just a constant, so I differentiate that part, is 0. We tidy this up, 2x cubed plus x. This is capital F prime, and that is equal to what we were originally questioned. So that's kind of a good check. For the first bit, it just ends up making sense to look at it that way, just to make sure that we're doing this correctly. As we get deeper into this process will start off being quite slow. It's quite a bit to get your head around in these steps, so no doubt that it's going to take a little bit of time and care when you're doing these questions. Negative exponents, it's going to behave just the same. So we're just going to have x to the negative 6. It ends up being useful to write it as that instead of over x to the 6. So let's antidifferentiate that. Negative 2/3 stays where it is. We add 1 to our exponent, so that's negative 5. And then we have to divide that amount out. So downstairs, we're also going to have a factor of negative 5. Minus, we have 1 over x. That's the derivative of natural log. So minus ln x plus 6. Add 1 to the exponent and divide by that amount. 6x to the 8 over 8. Last one, that's pretty straightforward. That's just going to be 3x and then plus c. Let's take a step and tidy it all up. Two over 15 x to the 5 minus ln x. Absolute value bars on this. Plus 3 x to the 8. 4. I'm just So that 3x to the 8 over 4 plus 3x plus c. To do a check on that. 2 over 15x to the 5 is the same as 2x to the negative 6 over 15 if you want. So this ends up being negative 12 over 15 to the negative 6. Or sorry, yeah, x to the negative 6. This was x to the negative 5 over here. Minus, so the derivative of ln x is 1 over x. The derivative of 3x to the 8 over 4 is plus 24 x to the 7 over 4. And the derivative of plus 3x is just plus 3. And then the c goes away. Just tidying this up. 12 over 15 negative is negative 2/3. The negative 6 minus 1 over x. 24 over 4 is plus 6 x to the 7 plus 3, which is equal to what we started with. So the check works. Careful about this next one. F of x equals cos x. We're not looking for negative sign. We just want positive sine x. The derivative of sine is cos. If this was negative cos, we would have negative sine as an antiderivative. So we'll just be careful about how that goes. Number 4, using along 2/3 sine x. So let's start this off by writing the 2/3. The antiderivative of sine is, well, the derivative of cos is negative sine, so this must have been negative cos before differentiating. X squared means I'm going to have x to the 3 over 3. 2 over x means we had 2 ln x, absolute, before differentiating. And then 1/2 is just 1/2 x. All of this, and then plus c. We can maybe tidy it up as at half a step. There's really not much to do other than we would maybe write this as negative out front. Negative 2/3 cos x plus x cubed over 3 plus 2 ln x plus half x plus c. All right, number 5. Okay, so this steps up a little bit here. Now we've got some chain rule going on. I'll differentiate. I take the antiderivative of cos 4x. This 2 just sits here. Cosine 4x. Cos is the derivative of sine, so this would have been sine 4x. But if I've differentiated sine 4x, I get cos 4x, but remember chain rule, we also have to multiply by the derivative of the inside. And so because in differentiating, I would be multiplying that by 4, so therefore, I have to divide this by 4. So being plus c, we end up with 1/2 sine 4x. C. So to see what happens when we undo that, take my derivative of 1/2. Sine 4 to the x, the derivative of sine is cos. So this ends up being cos 4x. But chain rule, we are now going to multiply that by 4. I take my derivative of the plus c, that's just 0, melts away. I simplify this down, 4 over 2 is just 2 cos 4x, and therefore this is equal to x. So we got it right. That was the original question. And then number 6. Kind of nice and easy. E to the 2x, the derivative of that. The derivative of e to the 2x would have been 2 times e to the 2x. So the antiderivative is going to be e to the 2x stays the same, but we have to divide by 2. And if I want to do a check on that, 1/2 is the over 2 part, e to the 2x. But when I differentiate chain rule, I also now have to multiply by 2. I differentiate the plus c, it goes away at 0, and all of this is just e to the 2x, which is our original. Okay, well, let's ramp this up a little bit. Vex, the negative 4/5 stays right where it is. The antiderivative of sine is negative cos, right? Because the derivative of negative cos would be negative sine. There we go. With brackets around here because it's not subtracting. And then we need to divide this by 2 because we would have chain ruled it. We would have multiplied by the derivative of 2x. So now we are dividing by 2. Our next term is going to be minus 3 e to the negative 3x. But chain rule, we're going to divide by negative 3. Plus cosine, the antiderivative of cos is just sine negative 3x, and then dividing by negative 3. We should tidy this up. Negative times negative, 4 over 10 ends up being 2 cos 2x. 5, or 2 cos 2x. The negative 3's in this next one divide out, and so this is just e to the negative 3x. Minus 1/3 sine of negative 3x. And that's it. Oh, plus c. That's it. Okay. In this next one, as these continue to get a little bit more interesting each step, root x plus cube root of x to the 4 plus 6th root of x to the 5, and so on. Probably a good idea as a first step to just write these as powers. Just write these in exponent form. This is x to the 1/2 minus x to the 4/3, x to the 5/6 minus 6x to the negative. So that's just rewriting my original function. Now we take capital F of x and antiderivative. Now, same rules apply whether we have fractions for exponents or whether we have negatives for exponents or straight up natural numbers for exponents. It doesn't really matter. We're still applying the same rules. So we are going to add 1. So this is x to the 3/2. Add 1 to our exponent and divide by that amount over 3/2. x to the 4/3, we add 1 to that, gives me x to the 7/3 over 7/3. X to the 11/6, 11 over 6. And then this last one is going to be minus 6 times. We're going to add 1 to the exponent. We had negative a half there, so now this is positive 1/2. See. Now, as we get experienced with this, you might skip that step and know that if you're going to be dividing by a fraction, let's instead just multiply by the reciprocal. So you might have called this 2/3 x to the 3/2 just as our first step, and that would have been just fine. Minus 3 over 7 x 2/3. We could also express these with radicals. 6 x to the 11/6 over 11, and then minus 12 x to the 1/2. Yeah, we possibly could have expressed those in radical form. When it gets really intricate in there with x to the 7/3, instead of calling it cube root, x to the 7, 6th root of x to the 11, that sort of stuff. I don't know. I think we're okay like this. Number 9. So the negative stays there. And the antiderivative of cos is just positive sine, right? Because the derivative of sine is cos. And so this is sine of x over 5. Now, we're going to divide it just like we were doing before. We're going to divide it by 1/5, which is the same as multiplying it by 5. So let's just slide a 5 in there. And in fact, in this next one, I'm going to write this as minus 2, but let's just hold up for a second. And let's take our antiderivative. Antiderivative of sine is negative cos. So this will be plus cos 2x over 3. And we're going to divide it by 2/3. So that's multiplying by 3 over 2. But the 2's will divide out. That 2 as a coefficient and the 2 in our denominator. And so the 2's divide away. It ends up being plus. And then we need a plus c on the end. All right, so number 10 is going to look like this. F of x equals 9,999,999 minus 9 over x cubed plus square root of x cubed over 5th root of x. We're probably going to take a step and so let's still call this lowercase f. I'm going to anti-differentiate it yet. Write this next term as 9x to the negative 3, but more so, we're doing this step for that last term. That last term is x to the 3/2 over x to the 1/5, right? So we need to do 3/2 minus 1/5. Now 3/2 minus 1/5 is 15/10 minus 2 over 10. So our exponent on x, this term is really x to the 13/10. And it's probably easiest if we write it like that first before we try to differentiate this. So our next step is now capital F. This first term is a constant, so when we Integrate that, it's that times x. No big deal. Next one, -9. We add 1 to the exponent. Be careful about this. When we have negative exponents, I see this all the time, that when we're adding 1, we end up going the wrong way. But adding 1 to -3 is -2. And let's divide that by -2. We add 1 to 13/10. 3 over 10. Divide by that. I'm probably going to need to simplify that a little bit, so let's take one more step. And x is equal to 9,999,999x. Can clean this up. Call it 9 over 2x squared. And then this last one is going to be 10 times 10th root of x to the 23, all over 23. Let's see. Let's see in there. All right, so there's a lot going on. There's a ton going on in these questions. And for sure, as you go through these, make sure that you're taking it slow and you're just going through this methodically, making sure each question has like 3 or 4 different questions inside it. These last couple, okay, so this kind of goes off in a bit of a new direction. And this is something that we are going to work towards getting to. But we need to think about what's happening with something like this. If we have f of x is 3x squared over x cubed plus 1, we can't just take the antiderivative of the top and of the bottom. It doesn't quite work like that. We've seen with quotient rule, like that would not create something like this. So there's something deeper going on in here. What you're needing to notice is that this x cubed, the derivative of that, the derivative of x cubed is 3x squared, which shows up here in the numerator. So we have both of those pieces kind of showing up in this question, x cubed and then the derivative of x cubed. And in fact, the derivative of x cubed plus 1 is 3x squared. So it's maybe helpful to think of it like this: 1 over x cubed plus 1 times 3x squared. So now, if we think of this as some chain rule happened here. We had an original function, we differentiated it, we used chain rule, and it gave us this. So it's like we had an outer function and an inner function. The inner function is x cubed plus 1. And so by chain rule, we differentiated it and got 3x squared. What is our outer function so that we have 1 over x cubed plus 1? I'll just pause for a second and think about that while I clean up my ugly f. So if we have the natural log of x cubed plus 1, if that's our outer function, remember that we need absolute value bars around that x cubed plus 1, and that's it. We can check that by differentiating it. Natural log would be 1 over x cubed plus 1. And then by chain rule, now we take the derivative of the inside. When we take the derivative of ln, the x cubed plus 1 stays the same. And then we take the derivative of the inside, so that's times 3x squared, which gets us back to our original question. So that was it. So some advanced thinking going on here, some pretty deep, you're asked for some good foresight and some good intuition about what's going on with this. We're needing to develop that and work with that. Maybe in this next one, f of x is equal to x cubed minus 2 all to the 4 times x squared. Okay, so we've got some chain rule. We wouldn't have product rule that gives us something like this. But this perhaps was chain rule of something. And when we think about it, if I differentiate x cubed minus 2, if I differentiate that, I get 3x squared. Now, I don't have 3x squared here, but I do have x squared. And so that part's critical, is that the degree of the inside of that function is x cubed. I take the derivative of that by chain rule, and that'll give me some amount of x squareds. So all that we're missing is the constant that we have to divide out. So let's look at that and see what happens. If our original function is f of x, maybe you want to write this in pencil so we can erase here in a second. But let's just play with this and guess what's going on with this. Maybe this was x cubed minus 2. If I want to anti-differentiate this, this would have been 5. Right? That would have been 5, that we would have multiplied that out front and then subtracted 1 to get 4. So if this was the case, then what would we have? If this was our original function that we're going to differentiate, what happens if I f prime left prime of that? Well, that 5 would come down front, the inside stays the same, and this becomes a 4. And then we multiply that by the derivative of the inside, which is 3x squared. So parts of this is correct. This part is all good. This part is all good. What's missing in our question here is this 5 and this 3. So what must we have had to have had? Well, we had to have had divided the 5 away. So when we anti-differentiate this, what we need in here is we have to divide that by 5. Just like we were doing before. When we added 1 to our exponent, we also divided it away. And because when we're doing chain rule with x cubed, we have to divide away that exponent also. So f of x, capital F of x, is not just the x cubed minus 2 to the 5. It's x cubed minus 2 to the 5 over 15 and plus c. X cubed minus 2 to the 5 plus c. That is our final answer. I would encourage you to maybe, let's take this, you take it a step further and differentiate that and make sure that we get back to our original question here. And that is it for 6.1. Good luck, ladies and gentlemen, and we'll see you in the next one.